Different ways of accessing the entire 8 bits. In the following code, as in many previous I/O examples, the entire 8 bits of port B are accessed. So if we take a look at the example code, we can see here that we're given a comment here, toggle all bits of port B. So we go through a couple of move commands, a delay, some move commands, and then we call our delay, and then we go into a loop. In this case, you can see we've gone through the same types of steps that we've gone through in the past. Literals with working registers to files, which become tri-states registers, in this case B. Then we end up moving a literal value x55 to working register 55H. Then moving to port B puts the 55H on the port B pins, and then we put another delay in there, and then so we're using these same relationships of 010101 101010 so that we can watch what's going on in the watch window in MPLAB, and then we go through our looping operation. So that's what we've seen up to this point. A different way of looking at the previous code toggles all of the bits of port B continuously. Another variation then of the code we can see, and we've seen this before, where we use a clear in the specific register, tri-state B. We do our move commands, we call our delay, and then we move again our complement AA to port B, call a delay, and then go into our loop. So that's what we've seen so far. The following now is another way of doing the same thing. So in this case, again, we do our clear register. We're going to clear the tri-state to make port B an output port. Then again, we move our literal 55 to the working register, and then we move that value to port B on the port B pins, and then we use a different command here, COMF, port B, F is the directions here. So we're going to toggle bits of port B by using this this complement. Then call the delay, and then branch. So the above code uses a technique that we call read, modify, and write. Due to timing issues, we must be careful not to have two I/O operations, one right after the other. And it's really hard to tell on logic devices if you're going to have a timing issue. Every device is a little different. Examine the following rewrite of an earlier code fragment in which the data was read from port C and sent to port B. Okay, so we've got we should have a piece of code here. There it is. Okay, so if we take a look at this, again, clear the tri-state buffer, make port B an output port, set the tri-state C, all ones to port C as an input, and then move to a specific file, port C, in a working register. So we're get the data from port C and moving it to the working register. Okay, and now we've got an operation here called NoOp. Okay, we need some NoOp to ensure that data is in the working register. Moving working register file to port B before it is sent to port B, we do a branch L4, and again we've got a loop to make it keep doing it over and over. So we use that NoP, that NoP value or statement to help control, to make sure we don't have data at the same time. So we need this NoP, NoP, or some other instruction to make sure that the data is written into the working register before it is read for outputting to port B. Okay, this is called a data dependency in the CPU design. This type of data dependency is commonly referred to as a raw, read after write. The NOP will introduce a bubble into the pipeline to remove data dependency due to a read after write. Okay, if we look at the figure 4.7 in your text, one way to avoid such a problem is to use the move FF instruction, which is a 4-byte instruction. This is coded as follows. So you can see we've got the move FF command down here. Again, we've done a clear of a file, the tri-state buffer, make the port B an output port, set the file tri-state C equal to FFH, port C input, then move FF, port C, port B. So we're identifying with that FF the file at port C, the file port B, and we get from port C and send to port B. Branch L5, and so with that, again, we end up looping per se. So if we take a look at the figure here, we can see what's going on in those sets of instructions as we look at what's going on in each of the registers with each of the commands. And you can see in the first one here, they're showing you that there's too short of a time period here to accurately know whether or not the information that was moved was the correct information, and it ends up becoming a timing problem. We're down here, we can see that we've extended the time a little bit with this NOP by putting a bubble in the pipeline, and then we've got our move of information from C to B. Okay, and you can see what do these represent. N for no operation, D for decode the instruction, R for read the operand, P for process, and then W for write. If we take a look at ports status upon a reset, upon reset, all ports have value FF in hex on their tri-state register. And you can see here in the table, upon reset, this makes all input ports the same, all ones, all ones, all ones. Note, all ports on the input ports are then reset.